So, okay, so yesterday we started discussing on objective analysis methods, and we talked about 4 5 methods of objective analysis. Among them were functional fitting method, empirical linear interpolation, successive correction method, Cressman's method, and Barnes scheme. Okay. We also mentioned that Cressman's scheme was the first scheme which was operationally used at the NWP center in USA in early 60s. Just a minute, I'm sorry, somebody is ringing my bell. I have to just interrupt for a while. Just 1 minute, okay? I'm sorry, yeah, I got interrupted. So, can you hear me? Hello?
Yes,
Yes,
sir.
sir. Yes, sir.
Yeah,
Yes, sir.
right. So, we discussed about 4 5 types of schemes yesterday. And today we are going to continue discussion on the last scheme, which is the optimum interpolation scheme. Okay. Among all of them, optimum interpolation scheme is most complex, and later on, initially, although Pressman's scheme was used for operational purpose in early 60s, starting with US Weather Service. But after that, most of the center around the world, including India, were using the optimum interpolation scheme. Okay. And the recent schemes which are now being used are actually based upon the optimum interpolation scheme. I mean, the concept is based upon the optimum interpolation scheme. We call it OI, or sometimes also the multiple optimum interpolation scheme, because of the fact that it uses the multiple observations and also multiple levels at the same time to optimize the result or to minimize the error. Okay, so optimum interpolation scheme. Now in this scheme, an ensemble average of the squared difference between the gridded and observed data is minimized using the method of least squares. The whole idea in the objective analysis, as we discussed yesterday, is that we try to minimize the difference between observation and the first guess to get a new analysis or updated analysis at the current time. Okay. So earlier when we discussed yesterday, we were discussing that at each grid point, we try to calculate the error. Okay. The error is the difference between the observation and the first guess. Okay, and then that is called the observational increment or prediction increment, and that we add on to the first guess or the background analysis to get the new analysis. So point by point we go. Whereas in the case of optimum interpolation, rather than minimizing separately at each grid point, we try to minimize the whole ensemble of the difference between observation and the first guess at all the grid points by using a least square technique. And in this scheme, actually, I mentioned that it's a very complex scheme. So today, be ready to see lots of mathematics, lots of statistics. A lot of statistical techniques are used to minimize the error over the whole grid point. Now, what are the steps? Steps are similar to what we taught yesterday. Like in step 1, values of the model fields are derived at each of the observation location using an objective analysis procedure that you are interpolating. Okay, using one of the objective analysis procedures which we discussed yesterday. For example, Fressmann's scheme. Okay, then the differences between the model-based values and the actual observation values, which are called observation increments, are obtained at each observation location. Okay, so at each of the observation location, we calculate the difference between background value and the observation. Then find out the weights that are to be assigned to each of the observation location in order to estimate the observation increment value at each of the model grid point. Okay, so we calculate the weights. Then the analyzed increments are added to the background values at each model grid point to generate new estimate of the variable. Okay. So as I mentioned yesterday that each observation is given weightage. Okay. And I also mentioned yesterday that the farthest observations are given less weightage, and the closest observations are given higher weightage. Okay. Weightage also depends upon the quality of the observation. Suppose some observations quality is not good. Okay, then we give less weightage to that. Okay. Then in mathematical form, this can be written as Fka is equal to Fkp plus summation of I is equal to 1 to n Wik Fio. Okay. Where Fa, all the superscripts with A indicates the analysis. In all the subsequent equations today we shall discuss, any variable having a superscript A will indicate the analysis, that is a new analysis. All the variables having superscript P indicate the prediction or the background value, you can say, or the first case value. Okay, and all the superscripts having O is the observation. Okay, now this K are the grid points. Okay, and I are the observation points. So you have n number of observation. Okay, Wik is the weighting factor for ith observation at the kth grid point. Okay, this is how it is. So as I explained, F represents a full-field variable. This capital F, and F represents an incremental. This small f incremental variable. That means incremental, that means difference between observation and the first case. The superscripts A, P, and O denote the analyzed, predicted, and background. Okay, and observed values respectively. The subscripts I and K represent the observation and model grid point locations respectively. The Wik, we use the pointer here. The Wik is the weight related to the observed increment. It is a weighting FIO for the analysis at grid point K. Okay, now the notations are. The novelty of this method is the derivation of the weights Wik through optimization. Okay. The optimum interpolation, also popularly known as OI, procedure determines the weights such that the mean squared error of the analysis is minimized when calculated over a statistically significant number of cases. Okay. So you are considering many observations around you, many grid points around you, and then together you try to minimize the observation, minimize the error. Let F, capital F, Kt is the true value of a variable at a given location. See, this is the thing, true. This is the crux of the problem. Like eventually our aim is to know the truth, okay, to get closest to the truth, okay, because we don't know what is the truth. Because although observations are considered to be truth, but even the observations have errors, right? All kinds of errors: manual error, instrumental error, transmission error. I mean, so many kinds of errors, as we have studied, discussed now in the initial lectures in this class. So, what is the truth? We don't know what is the truth, but our aim is to reach closer to the truth or closest to the truth as much as possible, right? So let us assume that ftk is the truth. K is the grid point. At any grid point K, let us say ft is the truth of the variable, whether it is temperature or specific humidity or wind or whatever. Let fkp is the first guess value taken from the short range forecast, that means the past 6 hours forecast. The observations FIO represent the existing atmosphere state. The objective analysis scheme, using the information from the first guess field and observations, produces another estimate FKA. So this is what we are aiming to get, FKA. So note that this FKA is the analysis. Okay, it is not the truth. Although this analysis we try to produce by minimizing the difference between the observation and the first guess, but still this is not the truth. The truth is this one, which is another estimate of FKT. This is just an estimate of the truth. Okay, it is not the truth, but it is the estimate of the truth. Thus, we can write the error associated with each individual value as analysis error, capital EA equal to FKA, okay, the first guess, minus the truth, right? Because the difference from the truth and the analysis is the error, right? And we want to minimize this error. Similarly, the observational error is denoted by EO equal to FIO minus FIT. And the prediction error is denoted by EP equal to FKP minus FKT. Okay. So these are the analysis error, observation error, and the prediction error. See, in this scheme, you can see how we try to minimize this now in an ensemble way, in an ensemble sense, using the least square technique. By assuming that the value or mean of these errors is 0, considering a large ensemble of samples, their statistical error estimates can be obtained as. Now, the analysis error estimate indicated by EA equal to this angle bracket is representing the mean, okay, of the square of the error, square root of the mean of the, like root mean square error. Similarly, the observational error estimate indicated by EO equal to again mean represented by the angle bracket, root mean square, this, and prediction error similarly EP is the root mean square of this one. Okay, where the angle brackets indicate the ensemble average. Now we normalize. Normalizing the various errors by the respective error estimates, we get the normalized error for the prediction equal to EP divided by EP with a arrow bar, EO epsilon O equal to EO divided by EO, and epsilon A equal to EA divided by EA. So these are the normalized errors. Okay, normalized errors of prediction, observation, and analysis. Similarly, the observation and analysis error estimates are normalized by prediction error estimate given by the normalized observation error is given by EO divided by EP, and similarly normalized analysis error is this one. Okay, we are normalizing by EP and EP. Okay. The observed and analysis increments will be represented in the dimensionless form. Okay, as FIO is equal to FIO minus FIP divided by EP, and FKA is equal to FKA minus FKP divided by EP. So these are the analysis increment and observational increment. This is observational increment and this is analysis increment. We say it increment because this is the difference from the observation of the first case and difference from the observation of the analysis. Okay, so this is the analysis increment and this is the observation increment. Observed increment and analyzed increment. We'll have to remember all these notations. All the subsequent equations will have these notations. The analyzed increments at point K is given by the summation of FAK. Okay, represented as FKA. The analysis increment at the point K is sum of all the observations I equal to 1 to n, the weighting factor times FIO. Okay, this is the observation increment. By substituting 413 this equation and this equation into the first equation that we saw, squaring and taking the ensemble average, the expression is derived for the error using the analysis at location K. And considering the relationships between the normalized prediction and observation errors. Okay, so we get after some manipulations the normalized analysis error variance at location K as given by this one. Okay, this is the normalized analysis error given by this expression 1 minus 2 times summing of all the observation points of the product of the HIK times HIK. The HIK is again defined here by this expression plus double summation, okay, for WIK, WJK, MIJ, where MIJ is again defined by this expression. Okay, long expressions indicating the error covariance matrices between the errors at point I and point K. I mean, they're trying to compute or consider the error of one location onto the other location also, because each points can influence the other point, both horizontally as well as vertically, right? So this, we are trying to be more and more realistic, because we are saying that observation error of a neighboring area can also influence at your point. If your neighborhood is not good, then somehow it will have an impact on your house also. It's like that. No? Because if your neighborhood is not so clean, then obviously it will have an impact on your house also. Similarly here also, if the neighboring observations are not good, then it will have an impact on the grid point of your interest. Okay, so considering the influence of the surrounding grid points on each other, the terms inside the angle brackets are error correlations. They are called the error correlations. Okay, for example, this EI, epsilon IP, and epsilon JP, and similarly epsilon IO and epsilon JO are the error correlation of the prediction at the point A, point I, and point J. There is a correlation between errors, prediction errors at the point I and point J. And similarly, this is the correlation of observation between the point I and point J. Okay, so these are the angle. Here, angle bracket is representing the error correlation. Earlier, angle bracket was representing the mean, but here it is representing the correlation between the neighboring points. Okay, of the errors of observation and errors of the prediction. So these two designate the prediction and observation error correlations respectively between the observation locations I and J. Am I audible clearly?
Yes, sir.
Yes, sir.
Okay, good. Yeah, I will keep asking because I don't know when I get interrupted suddenly. In practice, the observation and prediction errors are assumed to be uncorrelated. This is again a very important assumption here. But we are assuming that the errors between prediction and observations are not correlated. Okay. Which means that the terms containing cross correlations such as epsilon IP and epsilon JO, the cross correlation between prediction error and observation error between the 2 points I and J. Okay. In equations 17 and 18, these two equations are equal to 0, so they are not correlated. Okay. So we are assuming that. This is a very important assumption that the observation and prediction errors are not correlated. Okay, so all the cross correlations between I and j points are 0 in these equations. So this will make a lot of simplification. With the assumption that there is no correlation between the errors of the observations made at different locations, the observation error correlations such as epsilon IP and epsilon JO will be equal to either 1 or 0. For example, when I is equal to j, then it will be 1. No, and otherwise it will be 0. Then in this case, they are not correlated. These assumptions reduce the expressions for HIK and MIJ, which you saw in the previous slide. Okay, as HIK is equal to simply the correlation between I and K, kth grid point, ith observation point of the prediction, and MIK, okay, the correlation between the error correlation between I and J, the prediction, times plus EIO, the error at the ith point and observation point for the observation, times correlation between epsilon PI, epsilon OJ, which is correlation between I and J point for the prediction and observation, times EJO, okay, the error of the observation at the point J. The computation of Mij for all the I-J pairs L and N by N matrix M, in which the diagonal terms on row I is equal to 1 plus epsilon IO square. Okay, and the off diagonal terms on row I are equal to the correlation between epsilon IP and epsilon JP, which are the prediction error correlations. These prediction error correlations between location I and J. Okay, prediction error correlation, P is indicating the prediction error. Is a first case background fill. Now, at the point between the point I and J, and the other n minus one observations. That means you are trying to correlate the errors at a given observation point with all of the other observation points. Right? It's like saying that now there will be some correlation or some relationship between the observation at Jaipur and Delhi. I mean, physically, it's what amounts to. That you're trying to correlate between the observation at Jaipur and Delhi, or suppose Kolkata and Kharagpur, or say Chennai and Coimbatore, I mean, something like that for illustration purpose. Okay. Analogously, the calculation of HIK for all observations yields an n-dimensional row vector HK, designating the prediction error correlation between the n observation locations and I and the analysis grid point location K. Okay, so this is the HIK, which is basically yielding an n-dimensional row vector of HK. The essence of this optimum interpolation methodology is to determine the weights WIK, which minimizes the analysis error variance in equation 4.16. Okay, trying to determine the WIK. Earlier also, in other objective analysis method, now we discussed that it is the method, is the way how we compute the weightage for each observation is what is different from different techniques, whether it is a successive correction method or it is a Christman's analysis method or Barnes method. No, it is the way the weights are calculated. This is what is different. Here also same thing, that calculating the weight WIK weights IK now by minimizing the analysis error variance in that equation. And with any minimization problem, the equation 4.16 is subject to partial differentiation with respect to WIK for I equal to 1 to n observation points. Then equate the derivatives to 0 and solve the emerging set of n linear equations for the weights. The solution for this problem is given by WK equal to M inverse, that is a matrix, times HK, okay, where WK represents the n-dimensional row vector of weights WIK, and M minus 1 or M inverse 1, I can say M inverse 1, not minus 1, is the inverse of the matrix M. This means that the weight obtained by observation I for the analysis at grid point K is a function of three factors. Number one, the normalized observation error. Number two, the normalized prediction error correlations between the observation location and I and the other n-1 observation locations. And number three, the normalized prediction error correlations between the n observation locations and the grid location K. Okay. So in other words, we are trying to correlate between observational errors at all the grid points, the prediction errors at all the grid points, okay, and normalized values of that, of course, and the analysis also. Right. From this deduction, it can be inferred that the computed weights for the observations are dependent upon the designation of the observation error estimate EO bar and the prediction error estimate EP bar. Okay. And the prediction error correlations, they are the prediction error correlations epsilon p at the point II. If multivariate and three-dimensional data is involved, influence of all variables on any single variable and the influence of one level data on all this on the same or other variables at all other levels has to be considered. So this is what is the beauty of this scheme. In the multivariate optimum interpolation, we call it MOI. Optimum interpolation, popularly known as OI, but multiple optimum interpolation is known as MOI. Okay, and which we are trying to consider the impact of each observation on another observation or impact of one grid point on another grid point, both horizontally as well as vertically. Okay, and that's what is possible. I mean, in the nature also, that's what can happen. The atmospheric three-dimensional analysis may include variables such as the U and V wind components, the geopotential heights, and the height thickness. That is U, V, phi, and delta phi. Okay, delta phi is the thickness, phi is the geopotential. The analyzed geopotential height increments at a specified location is influenced by the nearby observed height increments and the observed wind and thickness increment. So what does it mean? That means each variable is impacting the other variable. The wind fields are impacting the thickness field and the geopotential, right? And that is also true in the nature, right? It's also true in the nature in the sense that if you just think that if there is a vortex or cyclonic circulation, the geopotential will decrease, right? It will have a lower geopotential because pressure will decrease there. So wind field is related to the geopotential. And once the geopotential will change, thickness will also change. Right? So in nature, all these things are interrelated, and so that's why we try to mimic the similar thing in the model also by representing different mathematical expressions. The performed analysis is multivariate and three-dimensional, implying that the observed increments need not be located at the same level as the computed analysis increment. That is, for example, wind increments at 250 millibar may influence the height in analysis at 200 millibar. See, this trying to just mimic the nature as much as possible as it happens in the reality. That means the wind increments at 250 millibar can influence the geopotential analysis at 200 millibar. Because of the multivariate three-dimensional nature of the analysis, the prediction error correlations relating different variables at different horizontal and vertical locations are to be obtained. Okay, so we have to obtain the prediction error correlations of different variables at different horizontal and vertical locations. And the prediction error correlation can be calculated, assuming that it can be expressed as the product of the vertical and horizontal components. The horizontal prediction error correlation is calculated between the geopotential height or thickness data at one location with geopotential height or thickness data at another location. The multivariate coupling is achieved by finding the appropriate prediction error correlation functions for various combinations of phi, del phi, u, and v observations. Okay. This ensures that the geostrophic relationship between the analysis increments of geopotential height and the wind is ensured. Okay. So by doing all these analysis through statistical calculations, expressions, eventually we have to ensure the physical relationship. Okay. For example, the geostrophic relationship have to be valid. It should not happen that by making all these calculations, mathematical expression, statistical expression, the result that we get is not in geostrophic balance, which is otherwise in balance in reality. So that should not happen. So in order to ensure that all the natural constraints like geostrophic balance or whatever conservation laws, they are all obeyed now after all these calculations or the statistical analysis. So we have to ensure that. Okay. The parameters that are to be determined are the observation error estimates EO bar, the prediction error estimates EP bar, and the prediction error correlations epsilon P, epsilon P. As described earlier, prediction error denotes the error values as assigned at a particular location due to errors of the forecast model. That is your first case. But models are not perfect, and the observation error represents both the instrumental error and the representativeness error. Measurement is simply not representative of features that can be resolved by the model. See how much care is being taken to ensure that all these statistical relationship assumptions try to be close to the reality. Okay, that means whatever instrumentation error are there, we have tried to account for that. Now, whatever is a representative error, like whether your observation is really representing the physical processes. Whatever observation, for example, you collect, say for example, Jaipur or Kolkata or Chennai or Delhi or whatever. For what process? Suppose you are trying to analyze the cloud processes. Is the observation representative of the cloud processes or not? Obviously, it is not, because of the lack of understanding of the processes or insufficiencies in theories in the models. So we are trying to account for those errors, representative errors. Also, representative errors means like suppose you are collecting the observation from a radiosonde, for example. You're launching the radiosonde, say at Jaipur or Delhi or Chennai or Kolkata, right? But by the time the radiosonde reaches 100 millibar or even above 50 millibar or 30 millibar, it would have drifted away by 200 kilometers. But still you call that radiosonde is representing the profile of atmosphere at Kolkata or Chennai or Delhi from where it was launched. Right? That's what you are assuming, that this radiosonde observation profile is representing the profile of Kolkata. Right? Representativity of the observation. Right? And of course, that occurs because in the upper level, our atmosphere doesn't change so rapidly, unlike at the lower level. Right? So if an incremental analysis scheme is both multivariate and three-dimensional, the prediction error correlations has to be defined three-dimensionally for that data increments of all different variables. Okay. The theoretical development for multivariate and three-dimensional variable is now considered. From equations 4.3 and 4.4, if you want to go back, you can see later on the slides. The equations 4.3 and 4.4, it can be seen that the observation increment for I, that is the location of observation, is also the difference between the observation error and the prediction error at the observation location, that is FIO minus FIP is equal to EIO minus EIP. Okay. Taking the product of the increments for observations I and J and averaging over a large ensemble, the covariance equations can be written as Cij, these big expressions, okay, covariance matrix, the product of the EIO minus EIP, the ith point and the jth point. okay, of the difference between observation and prediction error of the 2 points is equal to, again, this is EIO times EIO minus EIP times EJP minus EIO times EJP plus EIP times EJP, all statistical relationship. Because of the assumption that the observation error and the prediction error are not correlated, the cross covariance terms will be 0. Am I audible?
Yes, sir.
Yes, sir.
Okay. Yeah, good. Further, with the assumption that the observation errors are uncorrelated, limiting to only the horizontal component of the correlation, that is, observations at I and j are at the same vertical level. So for I not equal to j, you can write Cij equal to the error correlation of the prediction between I and j point. Anyhow, observation error correlation shall not be neglected when I is equal to j. So the variance of the increments at location I is given as Cii is equal to the average of square of the EIO plus EIP square of that, and which is represented as EIO square plus EIP square. Due to the assumption that the means of the observation errors and the prediction errors are 0, this equation indicates that the variance of the increments is equal to the sum of the squares of the observation, sum of the squares of the observations and prediction error estimates. This is the observation error estimate and this is the prediction error estimate. Squares of the observation error estimate and the prediction error estimate at the point I. Assuming that these error estimates do not vary with observation location. See, observations are varying, but we are assuming that errors are not varying. The variance of the increments for all observations can be expressed as C is equal to square of the EO plus square of the EP. Okay. The correlation Cij or C can be easily estimated. This estimate is biased because C contains contributions from both the prediction and observation errors. The normalized prediction error correlation, this EIP epsilon IP times epsilon JP, is estimated from the equation. Okay, this is the covariance matrix or error correlation between EIP and EJP is equal to the ratio of capital EIP, this is epsilon EIP, this is capital EIP times EJP divided by square of the EP. And similarly, Cij divided by C is equal to the ratio of this EIP times EJP divided by EOS square plus EPS square. Using equations of 26 and 27, these two equations, we can write ratio of Cij divided by C is equal to covariance matrix or error correlation epsilon IP times epsilon JP is equal to the ratio of this one, EPS square divided by EOS square plus EPS square. The calculation of the correlation will be biased by the factor R due to the term representing the square of the observation error equations in 4.24, and R is given by R is equal to ratio of the EPS square divided by EOS square plus EPS square. The correlation estimate Cij divided by C, this one, will approach R, will become equal to R instead of 1 as observation separation tends to 0, which is consistent. Okay. The denominator of equation 4.29 is simply the variance of the increments. Incremental observational error and incremental prediction error. Okay, variance of that. If the value of R can be determined, then these two terms, square of the error of observation and prediction, can be computed separately to segregate the variance of the increments as due to prediction and observation errors. From the data, the horizontal correlation Cij or C for observational increments can be estimated at various distances. By plotting these curves, the value of R can be estimated for each level. The function that best fits the scatter plot of Cij divided by C versus distance provides the horizontal height correlation function. To determine the value of R at each level, a correlation function is to be selected to fit the calculated correlations. For this purpose, several suitable functions are available. That is, ECMWF uses the summation of Bessel functions. The NMC Global Data Assimilation System uses a third order autoregressive function, TOAR. Okay, so different centers they use different functions. Okay, for this correlation function. The evolution of optimum interpolation OI in the late 1950s has led to the current data assimilation method for initializing the forecast models. Okay. So this is in a nutshell the theory behind the multiple optimum interpolation scheme of the objective analysis. Okay. So the whole idea or whole aim or objective of all these mathematical statistical correlations or expressions is that you're trying to get best fit of your observation onto the grid point, or trying to get your analysis at a given grid point which is closest to the observation. That is the whole idea. By trying to minimize the errors between the background field and the new observations which come at every time, like every 1 hour or every 3 hours or every 6 hours and so on, right? So you're trying to minimize the difference between the first case, which is the forecast from the past 6 hours, if it is 6 hour cycle, or forecast from the past 3 hours, if it is a 3 hourly cycle, or forecast from the past 1 hour, if it is an hourly cycle, like a repeat update data assimilation scheme. Now we use the hourly assimilation, but for global models, generally we use 6 hourly. Okay, hourly will be too much. And also we should have the hourly data available immediately to us, right? So generally, data like those from the radar, etc., they are available very frequently, and depends upon our capability of the center. Like, it requires so many things. Like to get so many data so frequently, it also requires a good bandwidth of the channel, right? The telecommunication channel that you are using. It requires a good bandwidth. In fact, in the initial days of NCMRWF, we remember that the bandwidth was not much. The bandwidth between the IMD and NCMRWF was not much. Actually, the bandwidth was also not between IMD's RTH and the next nearest hub. Now, if you recall that now the main telecommunication hub, MTH, or main meteorological center for this region is Tokyo. Like you remember that the whole globe has got 4 main meteorological hubs. Remember that Washington DC for the North America and South America, Moscow for the Europe, right? Tokyo for the Asia, and Melbourne for the Australia, right? So RTH New Delhi is directly linked to the Tokyo, because Tokyo is responsible for collecting all the observations and exchanging with RTH Delhi. The RTH Delhi in turn is connected to all the countries, nearby countries, Nepal, Pakistan, Bangladesh, etc., Sri Lanka, and all. So unless there is a very good bandwidth between New Delhi and Tokyo, we will not be able to receive all the data quickly on time. So how much data you can afford to assimilate depends on your bandwidth. And for a long time at NCMRWF, we had this problem because we used to see that the data which ECMWF receives, we are not able to receive that much of data because their bandwidth was good and our bandwidth was very poor. So a lot of time took to increasing our bandwidth. Now our bandwidth is really good. Okay. So I think we should stop here today. It's only 3:26. Okay, and we will continue the presentation tomorrow or discussion tomorrow on the data simulation techniques. Okay. Any question? We have got 3-4 minutes time today. Any question?
Sir. Yes, sir.
Anish. Yes.
सर फंक्शन है, आपने उसमें बोला कि बाउंड्री वैल्यूज के लिए पॉइंट्स नहीं लेने हमें, मतलब बाउंड्रीज वैल्यूज के लिए कैलकुलेशन नहीं करना हमें स्ट्रीम फंक्शन, राइट?
ओके।
तो फिर जब अगर कैलकुलेशन नहीं करेंगे तो वहां पे वैल्यूज 0 आनी चाहिए सर?
नहीं, 0 नहीं आएगा क्योंकि वहां पे तुम्हारे पास वर्टिसिटी है ना, वर्टिसिटी तो है तुम्हारे पास बाउंड्रीज पे, तो वर्टिसिटी है ना, वर्टिसिटी 0 है क्या वहां पे?
नहीं सर, वर्टिसिटी 0 नहीं है।
वर्टिसिटी
मैंने बाउंड्री कंडीशन लगाई, बाउंड्री कंडीशन में मैंने स्टार्ट किया 2 से, मतलब फर्स्ट को छोड़ दिया।
वो तो कैलकुलेशन के लिए कैलकुलेशन ऑफ द साई जो करोगे तो कैलकुलेट फ्रॉम 2 to n-1 पॉइंट। ओके
हाँ सर, हाँ बिल्कुल ऐसे किया मैंने। जैसे मेरा 61 है तो मैंने आई लिया 2 से 60, जे लिया 2 से 30।
ठीक है,
बिल्कुल इसी तरीके से किया, फिर मेरा आ गया मतलब जो कैलकुलेशन करके आना था। तो अब मेरा जो आएगा वो 2 से 60 तक आएगा और 2 से 30 तक आएगा, राइट सर?
हाँ बिल्कुल।
तो बाकी जो पॉइंट्स जो बचे बाउंड्री वाले वहां 0 आने, तो सर वैसा ही आ रहा है इसमें बाउंड्री पे एक,
वहां पे तुमने जो साई की जो वैल्यू है, साई की वैल्यू तुमने वहां पे प्रिस्क्राइब कर दिया है टू बी इक्वल टू से 1 × 10⁻⁶ मीटर स्क्वायर पर सेकंड।
हाँ
आइडियली क्या होना चाहिए? आइडियली होना ये चाहिए कि बाउंड्री पर तुम्हारा जो ऑब्जर्व्ड वैल्यूज है उसको रखना चाहिए, लेकिन तुम्हारे पास ऑब्जर्वेशन तो है नहीं, साई की ऑब्जर्वेशन तुम्हारे पास नहीं है, राइट? सो बाउंड्री कंडीशन पे तुमने एक एज्यूमशन डाल दिया कि चलो हमारा बाउंड्री कंडीशन पे वैल्यू कांस्टेंट है। इसका डेफिनेटली इसका असर पड़ेगा, इट विल हैव एन इम्पैक्ट ऑन योर वैल्यू ऑफ साई एट इंटीरियर पॉइंट्स, एट इनर पॉइंट्स, बट दिस फॉर द पर्पस ऑफ लर्निंग, purpose of calculation, you can start with that, because just see that whether it is converging or not. Haritasri mentioned that it took her 10 iterations, right, Haritasri, to convert?
No, sir, it converged in the first iteration, but then the plot was not looking good. So when I increased the number of iterations, the plot was looking better.
Oh, by increasing the iteration, plot was better.
Yes, sir.
So what was your threshold value? How much you took the threshold value?
Sir, I put 1,000 only.
So maybe when you increase that, it further improved. So maybe you can further reduce. Maybe I just gave an arbitrary value 1,000, saying that because the order of magnitude of psi is anyway 10⁻⁶. So if you are accurate at 10⁻³ maybe okay. But obviously, if you can further decrease it to 1, maybe go up to the tolerance limit of 1, then it will further improve. So Anish, do you understand? Yeah. So
yes, sir, I tried.
Yeah. So you took, you did some 10 iterations to get a better value, right? To get a better plot.
Sir.
Right, exactly.
Yes.
So maybe Anish, you can also take threshold value to be 1 rather than 10⁻³ and take the threshold value to be 1 between one iteration and
sir, it's too small. So like my so one, I think one will be too small.
One may be too small, maybe 10. Yeah, maybe 10. Right. So yeah, maybe 10 is okay, or 100, because 1,000 anyway you tried. So after 1,000 maybe 100.
So with 10 iterations, my difference values were about 200, 300 range.
Okay, so of the order of 2, second order, 10⁻², right? So take yeah, if you take further less value like 10⁻⁻1, then it will take more iteration, maybe 20 iterations. Maybe.
So I tried with 100 iterations also. I became slow. And but the plot, it just got averaged out, sir.
Oh, I see. After that, it doesn't differ much.
Yes, it shows colors, but then I couldn't see the features and all.
Oh,
it just got averaged.
Too much smooth.
I tried 30, 50, 100, everything. The 10 looked better.
Okay. So you had a very good numerical experience, numerical experience.
Yes.
Okay, good. Yeah, this is what the curiosity is now. We just look at how it looks like. That means after a certain point now, it starts smoothing things and you don't see the
Yes.
features, right?
Yes.
So I think reasonable value is maybe about 200 rather than about 3. And actually, the thing is that you are just learning it. Yeah, I know that does not give you the accurate distribution of stream function. I know that, but just for the purpose of learning that how to inverse the Laplacian, how to calculate the stream function based on the relaxation technique. This is the whole idea. It's a practical exercise basically is to learn how to write a program code to calculate the inverse of the Laplacian or stream function, right? So this whole idea is. And one more point, I thought I'll tell you, Anish, especially you were asking yesterday, do you have time? We have already exceeded time. Maybe we can discuss later on next class. But in a nutshell, yesterday you were saying that, Anish, that you since u is equal to del psi by del y and v equal to minus del psi by del x. So why not we directly calculate psi from u, right? That was your question yesterday. Anish,
Yes, sir. Yes, sir.
एक्चुअली क्या है कि हम लोग वहाँ पे कुछ मिस कर रहे थे बाय डेफिनेशन वहाँ पे एक्चुअली नोटेशन में इट इज नॉट द यू इट्स द यू साई इक्वल टू डेल साई बाय डेल वाई एंड वी साई इक्वल टू माइनस डेल साई बाय डेल एक्स दैट इज एक्चुअल डेफिनेशन बिकॉज योर ऑब्जर्वेशन इज द टोटल विंड यू एंड वी जो तुम्हारे पास है ऑब्जर्वेशन से दैट इज द टोटल विंड एंड टोटल विंड इज द सम ऑफ यू साई एंड यू काई if you remember the dynamic meteorology class, then
Yes.
we said that the wind, journal wind and meridional wind can be expressed as the sum of the divergent, non-divergent component and the rotational component. That means U is equal to U psi plus U chi. And similarly, V is equal to V psi plus V chi. Right? This is the total wind. So,
Yes.
and your observation of U and V actually is the total wind. It's not the U psi. U psi you are not observing. You are observing the total wind. Therefore, from that expression, you cannot calculate the psi alone from the total wind. Got the point?
Yes, sir.
We
Yes.
can discuss further. If it is not clear, I can discuss this on the Thursday class. Okay. So, ठीक है. So, very good. So, today we have to stop because we have a class at 3:30, right?
Yes, sir.
Yes, sir.
Yeah. Okay. See you tomorrow.
Thank you, sir.
Thank you, sir.
Bye.
Thank you, sir.
Okay.
Thank you, sir.
All right.
Sir?
Yes, Gitesh.
Hello?
Yeah, Gitesh, bolo.
Sir, I was running my WRF.
हाँ,
So,
तुम्हारा
while
क्लास
doing
नहीं
that,
है
I am stuck at some place. I don't know what to do.
तुम्हारा क्लास नहीं है क्या अभी?
Yes, sir?
क्लास अभी नहीं है, सेकंड क्लास नहीं है, नेक्स्ट क्लास 3:30 में।
Oh, yes, sir. कोई बात नहीं। इसमें मैं वो देख लूँगा।
तो बाद में डिस्कस कर लेंगे, ओके?